Okay, so in the last section we said that elements were made of atoms, but we didn't tell you what an atom is. So an atom is defined as the smallest particle of an element that retains the characteristics of that element. So if you take an element and you divide it into smaller and smaller pieces, eventually you get down to the size of one atom. And atomic theory was first summarized by Dalton in the early 1800s, so it's been a long time ago, but we still use his atomic theory, or at least a good portion of it. So atoms are very tiny particles of matter, much, much too small to see. We now have scanning electron microscopes that can visualize them. But even then, you just see kind of a vague outline. Atoms of one element are similar to each other, but different from those of other elements. So if I have an atom of carbon, it is fundamentally different from an atom of nitrogen. But all the atoms of carbon are similar to each other. Atoms form compounds in defined numbers. So you'll never have a compound that has half of an atom. Atoms do not occur in halves or quarters or eighths. You always have whole atoms. And they always are combined in defined numbers. So for water, always has one oxygen and two hydrogens. Hydrogen peroxide always has two oxygens and two hydrogens. And that's what makes it hydrogen peroxide and not water, because of the extra oxygen atom. Okay, the fourth thing is that atoms are never created or destroyed. So when we have a chemical reaction, the atoms that go into the reaction are found in the products of that reaction. They don't disappear or change in any substantive way. Not true in a nuclear reaction, but mostly we do chemical reactions. Okay. So, according to Dalton, an atom was the smallest possible piece of matter. And so everybody believed this until we came up with J.J. Thomson. And J.J. Thomson was working with electricity, and it was fairly new in the early 1900s. He was setting a high voltage on a evacuated glass tube. So there's very little air in this tube. And he noticed that there was a ray, a cathode ray, that traveled from the cathode to the anode. So it was going from the negative to the positive. And the ray was composed of very, very, very small particles. And he was able to determine the mass of the particles, and they were actually particles that were smaller than the atom. So Thomson had discovered our first subatomic particle, and he named it an electron. And he proposed a model for the atom that's called the plum pudding model. What he imagined was that there was a spherical cloud of positive charge, and it was studded with his electrons that he had discovered that were smaller than the atom, so they would fit inside, of course. And so this was the prevailing model when Rutherford did his experiment, his famous experiment with gold foil. It'll take me a minute to set this experiment up for you. Okay, so here we have a source of alpha particles, and they're going to be shot out of the lead box here onto this gold foil. All around the gold foil we have a screen, and when one of the alpha particles hits the screen, it makes a small thing of light. you're able to actually see the light as it hits the screen. Well, Rutherford was expecting that all of the particles would go straight through this cloud of positivity and hit the screen behind. So he was expecting that you would only get one thing of light here, directly behind the source. And instead, he found that most of the particles did indeed pass right through and hit the screen behind the gold foil. But some of the particles were deflected. Some of the alpha particles were deflected a bit, and some even came back at you. Rutherford was very puzzled by this. He described it as throwing a cannonball at tissue paper and having the cannonball come back at your face. And a new theory had to be developed to explain this gold foil. And this is the theory that he came up with, very similar to the theory we have now. In the center of the atom, there is a set of positive charge, and it's hard and dense. It's, I don't have any notes. Okay. So the nucleus in the center is positively charged, and it's compact and very dense. Around the outside, we have electrons that in mostly empty space. So when our alpha particles are going through, most of them pass through like this and go straight to the other side. Occasionally, though, we get one that hits that nucleus, and it will be deflected. Like I said, most of them, though, go straight through. And this new model was able to account for the new data that came up. This is the way science works. As we come up with a model, and then as we get new data, we reformulate the models. So this is the subatomic particle table. We have 3 subatomic particles. They are the proton. The symbol for a proton is a P with a positive charge. It has a positive charge and a mass of 1.007 AMUs. AMUs is the atomic mass unit. The proton is found in the nucleus. The neutron was also discovered by someone in Rutherford's lab. Symbol is N. It has no charge and has an atomic mass of 1.008 AMU. And it's also found in the nucleus. The electron, the symbol is E. It has a negative charge, and it is very, very small. It's 0.00055 AMUs. And you do not need to know these numbers. I would say that a proton is about 1, a neutron is about 1, and an electron is very small in mass. The electrons are found outside of the nucleus. Okay, just a little more about AMUs. AMU's official definition is 1/12 of the mass of a carbon-12 atom that contains 6 protons and 6 neutrons. So the electrons have such a small mass, we don't even include them in the mass of the atom. Okay?